Hi, I'm Mohammadreza Behrouzi. We are proud of ourselves that you watch our videos and we can make a small contribution towards your knowledge improvements. These videos that we have uploaded on our website or on our YouTube channel consist of notes and real case examples from our last projects. Those projects were performed by a team of professionals and experts. Therefore, by watching these videos, you can gain tremendous amount of knowledge and experience by which you can design your process units, your plants with highest safety. You are our only sponsor. So if you enjoyed the video, at the end hit the like and subscribe so that you can get informed about our latest videos. So to make you better understand how to use the equations and statements provided on API in order to size a PSV for a fire case scenario, I'm gonna provide you with the real case examples. With the real case, of course, this case, I sized the PSV for these applications during my last projects, and of course, this case was a fire scenario for wetted surface area. Remember, as I said, in fire scenario, we have two equations developed in API. The first equations was developed for wetted surface area, and the second equations was developed for unwetted surface area. You can go to my websites and download the episode explaining how to use API statement in order to size PSV for unwetted surface area. And but this episode is dedicated to better understand how to use API statement and equations alongside an Excel sheet to size a PSV for wetted surface area. So I'm gonna introduce you with the example with the real case. Here, as you can see, it is the PAN ID for a real case, and of course for a methanol plant, this is the oxygen line. The oxygen line before going to the oxygen before going to the reactor has to be preheated, of course, and has to be filtered and preheated. So here it is filtered, then it is preheated to the specific temperatures, and in these exchangers, these shell and tube exchangers, the oxygen is preheated with steam, with high pressure steams, and high pressure steam is after exchange of its heat to the oxygen is condensated, and of course the condensate produced here is accumulated in this drum, in these separators. But there is this possibility that this drum might be exposed to fire. Therefore, a fire scenario is defined for these vessels, because around these vessels there is a ATR, autothermal reactor, and of course the fire, if for instance, unfortunately, in some opposite situations, some fire gets out of this this reactor, it might impact this drum. Therefore, a fire scenario is defined for this drum. But since there are the fluid, but since this vessel, this separator contains fluid which is liquid, which is a steam, a wetted surface area is considered for these applications. So let's define our procedure. Our procedure consists of 6 steps. In first steps, we determine the scenario using API 521. In second steps, we calculate the relief load. In third step, we calculate the orifice area. And in fourth steps, we can select proper PSV type by checking back pressures. And in last step, we use API 526 to determine the designation and inlet outlet sizing for these applications. So in first steps, we said, as I said, it is exposed to fire. Then a fire scenario is defined with the equation for wetted surface area. Now let's have a look on the mechanical and process properties of these vessels. The diameter of the vessels is zero point 0.7 meters. The height is about approximately 3.2 meters. The fluid is steam condensate. The Z factor, the compressibility factor is 0.78. The ideal gas specific heat ratio is 1.09. The molecular weight is 18.02. The set pressure is 52 bar gauge. Relieving pressure, of course, we're going to calculate the relieving pressure. Don't worry about this ones. The accumulation is 0.21, and the material used is carbon steel. Since it is steams, it is condensate, it is practical, it is common practice to select carbon steels for these vessels. But about the selections of why the accumulation is 21%. In my first episodes about the general guidelines toward the design of PSV, I mentioned a table. I mentioned that there is a table in API. Here is the table. Based on these tables, we have two cases. If it is non-fire case or fire case. If it is a non-fire case, the maximum accumulations factor or percentage should be 10% for first relief device. For if you have multiple device installations, the maximum accumulations percentage is 16%. But if you have fire case like our case, if we have one relief device, the maximum accumulation percentage is 21%, 121%, as you can see here. So the reason why the reason why 21 0.21 has been selected here is based on that tables. And of course, I'm going to show you why relieving pressure is calculated in this way. But before calculation of relieving pressures, I'm going to introduce you with the Excel sheets that I have developed during my project. Of course, the same for all of these. This is the Excel sheet that I developed for fire cases, including unwetted and wetted surface areas for different vessels. And of course, for our case here, I've extracted the data from my project time. And of course, don't worry about this one. We're gonna create the Excel sheet from the scratch, from a starting point to the end point. And of course, after that, you can customize the Excel sheet for your applications. But here we're gonna it contains three parts. As you can see here, it is the in this part some information about the vessel is given. In this part, uh, some calculations are made by the Excel sheet: effective area, relief load, and all of these calculations. But here, before focusing on other things, we just want to right now calculate the relief pressures. You know that the set pressure is set pressure is 52 bar gauge. And by the way, the set pressure is equal to design pressure of the pipelines before that PSVs. So here it is, let's say it is done, and here I'm gonna create the Excel sheet for you. So it is doing. So the set pressure is 50-20 bar gauge. And how can I calculate relief pressure from set pressure? It is calculated in this way. V plus 1 plus the accumulated pressure, accumulated percentage, and multiply it by this, by the set pressure, then plus it by 1 to convert it to atmosphere, to convert to pressure absolute. So the relieving pressure is this value, 63.92, as you can see for yourself. So as I said, in API, two equations are developed, are dedicated for uh, vetted scenarios, vetted surface scenarios. If we have adequate drainage, we can use these equations. If not adequate drainage is provided in the size, then we have to follow these equations. Of course, we follow these equations because in the design basic, it is more conservative and we want to be more on the safe side. So we follow these equations. So in order to calculate this equation, to calculate the total heat, we set the C2 to this value for SI units. We need to calculate and F here based on the table I showed you uh, is considered to be 1, and we have to calculate exposure area. For calculation of exposure area, I'm going to show you a formula. As you can see here, for vertical vessels, for A vetted, this equation is used. This equation is a function of the diameter of the vessel and the height of the exposure. As I said, the height of exposures is, for instance, should be less than 7.6. Since in these vessels, uh, the height of these vessels is less than 7.6. Therefore, the whole height of the vessel is considered for as the exposure height for these calculations. So from tangent to tangent line is considered is as the height of these vessels, and here is about the head of the vessels. So all parts of the vessels is considered. So for calculation of total heat absorbed, we have C2 plus C2. We have exposure area, and we set F factor to 1. So in order to do the calculations, I'm going to open the Excel sheet, and of course create the Excel from a starting point. You know that this is the PSV. This is the name of PSV. You know that it is a steam and condensate, and of course compressibility factor from the data sheet is 0.78. Then we have ideal gas specific heat ratio, which is 1.09. Then we have molecular weight, which is 18.02. Then, of course, from the source of overpressure, of course, we know that it is fire and wetted surface. We have calculated relieving pressure. We know the set pressure, which is equal to the design pressure of pipeline. Accumulation 21%, as I described. And the thing that we need for our calculations here, we need to calculate we need to put information about diameter of the vessels. We know the diameter is this value, and as I said, the height of the exposure is about 3.27. As I said, the height of exposure is in fact the height between low tangent line to the up tangent line to above tangent line during design basic. So uh, I use this equation for calculation of wetted area and insert it here. But to save time, I make a pause and insert the equation here. As you can see, the equation is written down here, the exact equation that we just defined, and the exposure area is this value. Then, as I said, we need to we do not follow the first equation, we follow the equations in which we suppose there is no adequate drainage or firefighting system, and then C2 according to this equation is this value for SI unit. And F factor from table in API, it should be 1. Then we can simply calculate the total heat based on this equation, and I'm going to insert the equation here, make a pause and write down the equation. It equals as you can see here, the total heat absorbed by these vessels is this amount. Of course, it is in watt. So we have calculated the total heat absorbed. Now we have to calculate the relief load. In order to calculate the relief load, as you can see in Excel sheets, we need to use the simple equation for heat transfer, which is this value. The mass flow rate multiplied by the specific heat, which is this value. So since I want to calculate the mass flow rate, I have to divide the total area, total heat input to the vessels divided by the, in fact, the specific heat. So I have calculated this ones, and I need to have some information about the specific heat. Uh, a specific heat lambda ratio is this value. So I need, in order to uh, uh, calculate the relief load in kilogram per hour, of course, I need to make some conversion between watt and kilojoules. So here I'm gonna do the calculation here. It equals the heat input, and of course divided by the lambda ratio. So if I do these calculations, I'm not gonna get the relief load in kilogram per hour. So I have to take into account the conversion between watt and kilogram, conversion between kilojoule and watt, which is this value. So the relief load here is this value. Now that we have calculated the relief load based on the equation I inserted in the Excel sheets, the relief load became this value. Now we go to the third step, which is the calculation of orifice area. In API 20, in API 520, there is a sections about the critical flow and subcritical flow. And for each of the critical flow and subcritical flow, uh, uh, an effective orifice area calculations has been developed. And of course, based on these equations, we determine whether our system is in critical flow or subcritical flow. So after uh, calculation of this term and multiplying by upstream relieving pressure, we can calculate in fact, the critical flow nozzle pressure. After calculation of flow nozzle pressure, critical flow nozzle pressure, we compare the back pressure with the critical flow nozzle pressure. If the total back pressure is less than the critical flow nozzle pressure, then we are in a critical flow, or if otherwise, we are in subcritical flow. So we're going to do the calculation here to determine whether we are in a critical flow. And if we are in critical flow, we can use these equations. So here I need the cofactor. So here I write down PC to P1 equals so I have calculated this ratio. Now I need to calculate the critical flow nozzle pressure. So PC becomes this value. Multiply this by the relieving pressure. So the back pressure could be maximum this value. If the back pressure is more than this value, then we experience a subcritical flow. But since the back pressure is 21 and is less than this value, therefore we are in a critical flow. And since we are in a critical flow, we can use these equations. This is the effective orifice area calculations. It is dependent on different parameters: the weight calculated, the relief load, the temperature, the Z factor, the molecular weight, and the C factor, and relieving pressure, opposite relieving pressure, and different types of car. Of course, we're gonna talk about every parameter here. For we have different cofactors here. Chi is the coefficient of discharge. For preliminary sizing, use the following effective values. 0.9975 when a PRV is installed with or without a rupture disc in combinations. 0.62 when a PRV is not installed and sizing is for rupture discs in accordance with these sections. Since we install a PRV, 0.975 is selected as the value for CAID. Then we have CAIB. CAIB is the capacity correction factor to the back pressure. This can be obtained from the manufacturer literature or estimated preliminary sizing from figure 31. But here it says for conventional and pilot operated valves, use a value for CAIB equal to 1. So for preliminary sizing, we're going to use 1 for CAIB, and CAIC is the combination correction factor for installation with a rupture disc opposite of the PRV equals 1 when a rupture disc is not installed, and equals 0.9 when a rupture disc is installed in combination with the PRV. So since in our case we don't have a rupture disc, we select 1 as the value for CAIC. So far here, CAID is 0.975. CAIB is equals 1, CAIC equals 1, and 3 parameters is selected. Of course, in previous step, we have determined the relief load, which was this value, and of course, molecular weight, Z factor, and temperature, relieving temperature, all of them are crystal clear to us. And of course, we have determined the opposite relieving pressure. The only factor here that is missing here is C factor. C factor here, as you can see here, is a function of ratio of the ideal gas specific heats of the gas or vapor at inlet relieving temperatures. The coefficient is determined as follows. For SI units, we use these equations. So I'm going to use the Excel sheet here and calculate the effective orifice area. Of course, I'm going to delete all of this. Here is the effective area. In order to save time, I'm going to make a pause and write down the equations. But before going to the right to insert the equation, we need to write down some parameters, the cofactors here. CAID, for instance, should be this value, as we talked about it. And the core value, as we stated, is this value. And temperature, relief temperature, based on the Aspen Heises calculation, is this value. And of course, as I said, we need to determine the C here. C, as you can see, is a function of a specific heat ratio. I'm gonna write down the equation here, the exact equation provided in the API. So it is the C here. It is the C factor. And now I have the C here, I have the CAID here, I have, let's say, the mass flow, relief load here, Then I have the temperature here. I have the molecular weight, the compressibility factor. All of things are set. Therefore, I can use the equation provided in API and calculate the effective area. So as you can see, the equation is inserted and it is a function of, as you can see, C factor, mass flow rate, and all of the parameters I mentioned and talked about. And now that we have determined effective area, we go to the third, fourth step. In API, use API 520 to determine the designation and inlet and outlet sizings. In API 526, there is this table, these important tables, effective orifice areas. For different effective areas, a designation is allocated. For instance, for 0.11, the D designation is allocated. For instance, for 1.8 inches, card designation is allocated. For the largest font, 26 inches, T designation is allocated. And for PSVs, when we have a PSV in PNID, let me show you some PNID, some PSVs. For instance, this PSV. There is a PSV installed here on the vessel, and of course, uh, process engineers are supposed to write down these designations. And what does it mean? 1.5 G3. It means that the inlet of the PSV is 1.5 inches. The orifice designations, the effective orifice designation area is G, and of course the outlet sizing is 3 inches. So the G is, so the effective orifice area for that PSV is 0.5. So at first we decide which designation is allocated to our PSV. Then after designation, after finding the right designations, we go to the table corresponding to that designations. I'm gonna talk about it a lot. Don't worry about this one. So the calculated orifice area for our applications is about this value. Uh, but remember, it is calculated in millimeters, powered by 2. We have to convert it to inch. So here in millimeter, in inch. To convert it to inch, I have to divide this by the conversion between inch and millimeter. So it is in centimeter. So this value is our calculated value. And of course, remember, in API 526, all of these are in inches. So we have to convert them in inches. And that was the reason why I converted to inches. So this is, now I compare. So this one is less than this value. Therefore, the selected, the designation here is the D designation. So we know that this is D designation. Now we go to the tables. In after this table, there are some tables for each of these designations, for each of these effective orifice areas. In these tables, at first I'm going to describe this table here. It it is composed of different sections. The first section is the material of the body and bonnet. You have to select a material for body of the bonnet. And here we have the inlet and outlet ASME flange class or rating based on temperature and pressure ratings. You have to see the inlet temperature and pressure rating for your application and outlet that, and select one of these one. For instance, for one of these applications, 300 pounds and 150 pounds are selected for the temperature and pressure rating. So this one is selected, the third row is selected. Then we have here the maximum inlet flange pressure limits against, against temperature ratings for conventional and balanced below valves. Remember that we have, in other parts of these APIs, the tables for pilot operated valves. Here, this table is for conventional and balanced valves. So before going to these tables, you have to determine whether the type of your PSV is a conventional or balanced below valves. So you select the operating the relieving temperature. For instance, it relies in this area. So you have to you have selected the third area, third row, and you find the intersect, which is this one. It means that 600, approximately 600 psi is the maximum set pressure for inlet flange that can tolerate. So we know that for our application it is a D orifice, but before uh, using this table we should make sure that our valves is a conventional and balanced below or balanced type. To do so, we go to our application and check it. According to licensor data, superimpose and barrel back pressure maximum 25 bar gauge. Even though selecting conventional type is not fully recommended, conventional type has been selected by the lessor. Of course, during project types, we talked to the manufacturer of these valves, and of course, they said that even by this high percentage of back pressure, our PSV is able to operate well during such stringent and strict conditions. But by the way, if you want to know how this table works, it's a good guidelines for preliminary sizing and preliminary selection of the type of PSVs. Of course, as you can see here, the total back pressure here is 40% of the set pressures, and of course, since the back pressure is constant, we have different back pressure type: constant type, variable, superimposed, and variable build up. R type is a constant type because there is no upper of that one to change the back pressure of the to impact, because it is discharged to the atmosphere, and there is no restrictions in order to change the back pressure, the total back pressure. Therefore, the back pressure type is constant, and since the it is 40%, it lies in this area between 30% and 50%. Based on this table, it is better to select a balance type, but the manufacturer told us, promised, and guaranteed that even if conventional type can operate under such condition. And of course, we selected the conventional type for our applications. So we know that it is a conventional type. So this table could be used. And of course, since it is in esteem, since the fluid is esteem, it is a common practice to select carbon steel for esteem condensate of water. When we have condensate of water and let's say a steam condition, in normal conditions, we select carbon steel as the material for PSV. So we select this one. And right now we need to determine the inlet and outlet class. We go to the piano ID, as you can see here for yourself. The In the designation here, you can see the F24 and B24. F24 means in pianoides, in most pianoides, means 600 pounds, and B24 is the carbon steel, is a designation for carbon steel, and F and B is F is for 600 and B is for 150 pounds. So we are supposed to select the fourth row, this row. Right now we have to check the temperature rating. In order to do so, the relieving temperature is this value. Then in order to convert it to Fahrenheit, I use this equation. So it is about 554 Fahrenheit. So it is more than this value, but less than this value. So it lies in this column. And the intersect between the fourth row and this column is this value. So the maximum pressure that the inlet flange can tolerate is 825 psi. And right now I have to convert the set pressure to the set pressure uh, to psi, from bar gauge to psi. As you can see, it is less than this value, therefore this type is selected. Therefore, a PSU with the designation of 1D2 is selected. And this is the final sketch for our application. Now, let's have a review on what we have done. In first step, we determine that since it is exposed, there is a possible exposure to the fire. Since there was a reactor near these vessels, we said that a fire scenario should be defined. And since the fluid inside the vessel was a mixture of steam and condensate, we followed the equation for wetted area, wetted surface area, for calculation of relief load and effective orifice area. Then we used, based on API, at first we calculated the total amount of heat absorbed by the vessel by using this equation. Of course, we had this equation and these equations, but we followed the second equation since it was more conservative. We uh, didn't take into account any fighting equipments or drainage systems. We based our calculation on the fact that there is no adequate amount of drainage. Therefore, we tried to be more to appear more conservative. We used this equation and calculated the total amount of heat absorbed by the reactors, and after that we use the specific heat of the steam, and of course use the simple equation between mass balance, the specific heat, and the total heat, and calculated the relief load. After calculation of that, we calculated orifice area based on the relief loads. We at first determine whether our flow is in a critical situation or subcritical. We use this equation. We calculated this equation, this ratio, and then decided that it is in critical conditions. Since it is in critical conditions, we can use these equations. We use these equations and of course define different cofactors based on these definitions here. And we had the three living temperatures, Z factor, M factor, the molecular weight, and of course we have calculated, for instance, relief load in previous steps, and all of things were set and simply calculated the orifice area, and we converted the orifice area to inches then, and used API 526 and used designation table to find the proper designation for our application. It became the this designation was selected, and then after that we went to the tables and checked whether the designations with this PSV can tolerate such conditions, and hopefully it was able to withstand to tolerate such pressure ratings. This is the end of our episodes. I hope that you have enjoyed every moment of these episodes, and I wish you good days. Have a good time.
Hi, I'm Mohammadreza Behrouzi, the manager of Educational Institute for Equipment and Process Design. I hope that you have enjoyed every moment of this video. I highly recommend you watching videos instructing heat exchanger designs from our websites or through our YouTube channel. By watching these videos, you become not only familiar but also professional in thermal and mechanical design of shell and tube heat exchangers. So far, if you have enjoyed the video, hit the like and subscribe.